Okay, so we're jumping into a new topic, moving a little bit beyond reactions, but we're going to look about energy and how we incorporate energy into analysis of different chemical processes. And really this concerns thermodynamics. So thermodynamics, just listed a definition right here, is the branch of science or engineering for that matter that deals with heat, temperature, energy, and work. So it's the set of rules or laws that govern how energy is transferred or energy moves or how energy affects different objects and so forth. And really, to work with energy, we need to understand some concepts of thermodynamics. So here's some examples where thermodynamics is important, just from a chemical engineering standpoint. First one is heating here. And heating can involve many different things. It can involve cooking. If you've done cooking, you've heated something, and that's the transfer of heat to make something hotter. Separations, for instance, distillation is something that we've done before for material balances, and that requires energy to initiate these processes. Reactions. So we've dealt with combustion reactions, and combustion reactions produce a lot of heat. And that falls into the realms of thermodynamics. Where does that heat, how much heat is going to be produced, and where is that heat going to go, and so forth. When we're dealing with phase changes, when we have a liquid such as water and we boil it, or we take ice cubes and we melt them, or any other material, that deals with thermodynamics because that deals with the transfer of energy to initiate these phase changes. Electrical generation, electricity is just energy in the form of electrons. So it deals with thermodynamics and so forth. And we could just keep listing these all day long, different examples where thermodynamics is important. And in reality, almost every single chemical process involves thermodynamics at some level. Where is the energy going and coming from, and how does that affect the process we're studying? So we need to talk about units of energy. So units of energy are typically kilojoules, joules, BTU, horsepower. These are units of energy, and we've dealt a little with them before. These two here on the left, kilojoules and joules, are SI units. These units over here are non-traditional units that we may encounter, English system and so forth. But we can easily convert between the two, or these various units, just using our conversions. We also need to talk about the concept of power. Power is simply energy per time. So a typical unit would be a joule per second. And that's also known as a watt. So when you'll look on some of your electrical devices, it might say 300 watts or 200 watts. Or we talk about a light bulb, and a light bulb, maybe 75 watts or whatever. That just tells us how much energy it takes per time. So you could, in principle, if I turn on a light bulb for an hour, I could figure out how much energy it used for that hour by using its wattage. So if it uses 200 watts, that would be 200 joules per second. Then I could convert that based off of 1 hour of usage to how much energy it used. And so we just need to take that into account when we're dealing with energy and thermodynamics. Let me just say that oftentimes we're dealing with flowing systems. So in that case, we might have our energy in terms of energy per time, just like here. So we just need to be aware of that. That's certainly possible, especially with a system that's flowing. So the first thing we want to talk about is heat. Heat is such a basic concept, but we need to make sure we clearly understand what it is, because it's fundamental to what we're going to deal with and work with in this course and other engineering courses. So heat, more or less, as I've defined here, is energy associated with temperature. And right here I say that heat normally transfers from a high temperature to a low temperature. So, for instance, if I go outside and make myself a little campfire here, there's a lot of heat that's being generated by that campfire. And that heat is being transferred. It's going from this hot fire to the surrounding air. And that's why if you stand by a fire, you're going to get hot. It's going to be giving you heat energy. That fire is transferring from hot temperature to low temperature, the surrounding air, or yourself, the body. Also, it's intuitive think about what happens if I put out a bunch of ice on a table. So if I put this ice out on a table, what will happen? Well, if I let it sit for an hour or two, it will melt. It will turn into liquid water. And this is because it's heat transfer. In this case, the surrounding air is a higher temperature than the ice, so heat will be transferred from the surrounding air to the ice, and that heat energy imparts to the ice and melts it. It doesn't happen in reverse. We don't see heat being transferred or energy being transferred from the ice to the surrounding air. We see instead that heat or energy from the air transfers to that ice. And so that's another idea of the heat energy. Key concept, just remember that whenever you have something hot and something cold, there will be heat transfer from the high temperature to the low temperature. Next concept we want to talk about is work. So we talk about work in a colloquial sense, and oftentimes we may say something about it, but we want to get exact about what it means. So work is essentially any energy transfer across some boundary that is not heat. If it's heat, then it's not work. Kind of a weird definition, but if I have some energy being transferred from one body to another, for instance, if I'm touching something and I'm imparting some energy to it, and again it's not heat, that's work. A typical definition is work is energy transferred due to a force acting over a distance. So if I push something, I'm doing some work to push that thing. And here's different types of work. So the first one is a pressure volume change. If I take something and I squish it down, like I take a flask of gas, say of air, and I push it down to make it a smaller volume, that takes some work to compress it down to a smaller volume, and that's a pressure volume change, a compression. Shaft work, this is basically spinning something, so it takes energy to spin something. And this is important especially for electrical turbines where we spin them to generate electrical energy. But it takes energy, shaft work, to spin that turbine. And that's just the shaft motion spinning around in a circle. That's shaft work. Spring work. So if I have a spring, and I compress it, it takes work to go ahead and compress that spring. And that's work that I'm putting in it through, or energy I'm putting in it through spring work. And then there's electrical work. If I have electricity flowing, it carries with it some electrical energy, and that electrical energy can power electrical devices, whether it's your phone, your iPod, etc. So that's kind of our short introduction to thermodynamics. Key concepts we just need to realize is that energy is moving all the time. It's moving back and forth between different bodies, whether those are people, machines, whether those are chemical bodies, one chemical and another chemical. There's always energy transfer going on. And that energy transfer can be heat, which is temperature differences, or it can be work if one body is pushing on another or inducing some sort of movement or force on it.